Yesterday we were talking about projectile motion. We ended off the day talking about projectiles that are projected horizontally. Okay? What are a couple of things we need to remember about a projectile that is projected initially straight horizontal? The initial vertical velocity is 0. So with all projectile motion problems, I want to split it up into horizontal and vertical component. What's the only thing they share? Time. Okay? The only thing that they share is time. So from a vertical perspective, if I've got something that's projected horizontally, the biggest thing I have to remember is that the initial vertical velocity is 0. Certainly there are other things I need to remember, but they're fairly commonplace, like the acceleration is 9.81 meters per second squared, okay, stuff like that. All right, so I want you guys, with that little piece of information, all right, to try and solve this problem. So a ball rolls off a table. That means it rolls horizontally off the table, okay, and it hits the floor 0.85 meters from the base of the table. All right, so this table is 1.2 meters tall. I want you to calculate the speed it rolled off at, which is the horizontal velocity. All right? So, to help you out, let's finish off our givens here. Okay? The rest of our givens are acceleration for the vertical part, because obviously it's not accelerating horizontally. The vertical displacement and the horizontal displacement. Okay, that is all the information we know. We're trying to calculate the horizontal velocity. Give you a few minutes on that. Okay, what should I calculate first? Time. Yeah, I should calculate time first, because really at this point, it's all I can calculate. Okay, I don't have enough information from a horizontal perspective to get V yet. Okay, so what I have to remember here also, guys, is that when we're talking about the horizontal part, we're talking about something moving at a constant velocity, so we can use V equals d over t. When we're talking about the vertical part, we're talking about accelerated motion. V equals d over t is out for that. I have to use one of my acceleration formulas. Okay? In particular, for this one, I'm going to be using d equals vi times t plus 1/2 at squared, but since vi is 0, I can just get rid of that part, because in 0 times anything is 0. Right? So I'm going to plug in manipulate my formula first. Right? And I think I confused a couple of people yesterday, because yesterday when I was manipulating this, I was manipulating it so it looked like this. T equaled the square root of 2d over a. And people were looking at it and go, where are you getting that 2 from? Okay, well, when you divide by 1/2, it's the same as multiplying by 2. Now, I could also write it this way, and it would be equally correct. Whichever way makes more sense to you is fine with me, because it works out to the same answer regardless of how you do it. Okay, so if I confused you yesterday when I did that, my apologies. I didn't mean to. I just was thinking the way my mind works, and I forgot all about it. I had never talked about that. Okay? Now I'm talking about it. Now it's out there. Okay? All right. So if I'm plugging in these numbers, then okay, we've got 1.2 meters. That was our vertical distance. Okay, divided by 1/2 times 9.81. That'll get us our time. So square root of 1.2 divided by, now here's the kicker with this one, is we do have to put the bottom in brackets, otherwise it'll do order of operations, which we don't want. All right, so this is taking about 1/2 second, 0.494 seconds, or 0.495 seconds. All right, that can come over here, because time is the only thing the vertical and horizontal parts share. Now I can use the t in a v equals d over t calculation, 0.85 divided by 0.495, and we're going to get 1.7 meters per second. Okay. Everybody all right with that? Okay. All right, that's the velocity of rolling off that. Any other questions on that one? So with horizontal projectiles, there's only a couple of things I can ever ask you to calculate. I can give you the right set of information to ask you for the height that it falls from, the right information to ask you to calculate the speed it rolls off at, or how far it hits from the base of the object, the horizontal distance traveled. Those are the only three things I can ask you for in a horizontally projected question. And we've gone over now, I think, 2 examples of each one. Okay, so there's really nothing else that I can show you under those. All right. Today, we want to look at projectiles that are fired, launched, whatever, at an angle. So if I launch something at an angle above the horizontal, what's its path going to look like? Exactly, it's going to look like an arch. Okay, it's going to do this. Okay, and it'll hit the ground a little ways away. Now, you probably realize this if you ever played with the hose when you were a kid. Maybe you still do. Okay? But if you were trying to spray somebody with the hose and you needed the water to go a little bit further, what did you do? Besides increase the flow. Lift it up. Just angle it a little bit. If you angled it a little bit more, the water went further until you got to 45 degrees and then it started coming back to you. Okay? Beyond 45 degrees, right, it's going to start moving back towards you. 90 degrees and you're just getting wet. Okay? All right, so we kind of have that experience. Okay, if you're throwing a ball, okay, or any other object, playing catch, you know, regardless of how fast you throw it, it's never on a rope. Okay, it's never like perfectly straight. Right? There's always going to be some amount of arc. Now, the faster you can throw it, obviously, the straighter that trajectory will be. But even like professional football playing quarterbacks are not throwing a ball on a straight line. Okay? It's always going to have some small, at least, amount of arc, depending on how far it has to travel. If it's a Hail Mary bomb, okay, that's nearly the length of the field, then it's a high arcing, okay, shot with a long hang time. Same with if you're doing a kickoff or a punt or something like that. Okay, the ball travels in that arc. If you're playing golf, same idea. Okay, it travels in a long arc. Okay, and if you hadn't noticed, when you're playing golf, different clubs are angled differently. Okay, the whole purpose of that is to change the launch angle. Okay, flatter irons, like a 2-iron or a 3-iron or a 4-iron, have very small angles of departure. Okay, so you hit them further. Okay, your sandwich is angled at like 55 or 60 degrees. Okay, and so you can just about cut right underneath the ball and flip it right up. In fact, it's called a flop shot. Okay, and some professional golfers will use it to get out of a sand trap. Okay, they'll hit the ball and it'll almost come right back down on top of it. Okay. Now, you obviously wouldn't want to do that because then you take another stroke. It's still in the bunker. Okay. They don't go very far forwards if they're angled even more. Okay. Everybody all right with that idea? Okay. So there's still 2 parts to something being launched at an angle. There's still a vertical part, and that's still going to be experiencing accelerated motion. And there's still a horizontal part, and that is still traveling at a constant velocity, so v equals d over t. Those principles don't change just because now we're launching something at an angle. If we're launching something at an angle, now the initial vertical velocity isn't 0, because now at time 0, it is actually moving up or down, usually up. Okay. Everybody with me so far? Okay, so here's what happens with a projectile launched at an angle. this would be my projected velocity, this arrow. All right, so that would be how fast it's launched. All right, so if it's somebody throwing a ball, okay, let's say it's 20 meters per second, which is a pretty good throw. The horizontal component of that represents the horizontal constant velocity. How would I calculate this number if I know, let's say that this is thrown at, let's just say 30 degrees, okay? How would I calculate V horizontal? Trigonometry, exactly, okay? Exactly what we've been doing in all of our vector addition. This is the adjacent side, so I would calculate it using cos, okay? Because cos uses the hypotenuse and the adjacent side, right? So I would calculate V horizontal by going cos of 30 times 20, okay? And that would tell me how fast this thing is moving horizontally throughout its flight, right? This side represents my initial vertical velocity. How fast it's moving straight up and down at time 0. That would be calculated using sine. Okay. So nothing you haven't done, it's just finding x's and y's. Okay, you know how to do that already. Things that are new. Obviously for our horizontal parts, we're dealing with v equals d over t. Okay. For the vertical parts, it could be any acceleration formula depending on what we have. Right? We've obviously got VI. Okay. We also have A. But now I'm making a negative. Why? Right, there's up and down. When we were doing the horizontally projected ones, the only vertical movement was down. Okay, it was never launched at an upward angle. This is launched at an upward angle. So its initial vertical velocity is up or positive, so I need to make the acceleration now negative. Right? So I would have those pieces of information. I would have one more piece of information if the launching point and the impact point are the same height. Okay? So it's on a level piece of ground, like a football field. Right? So it's a nice level piece of ground. I would also know VF. What would VF be? It's not 0.
Same as VI.
Same as VI. Okay? Exactly what we talked about the other day. If I throw something up in the air and it comes down to the same height I threw it from, it's got to be going the same speed I threw it at because the acceleration and the distance are the same up and down. It has to come back at the speed I threw it at. So VF would be negative VI. Okay, so VI in this case is 10 meters per second up. VF is going to be 10 meters per second down, or negative 10 meters per second. So then I would know VI, A, and VF. What can I calculate with those three things? I might be able to use it over there. Okay, I can calculate displacement, but here's what it's going to be. 0. Time. Yeah, okay. Why is my displacement going to be 0 if I use VI and VF and A in this situation? Right, start and end are the same, right? Goes up, comes back down, this vertical displacement is 0, right? But I can calculate the time, and I can calculate that using the formula you used last year. And once I have time, time can be used over here with the horizontal information. A question like this is going to ask you for three things. Total time, which we just looked at how we would calculate. Horizontal distance traveled, and the maximum height reached by the object. Okay? So to calculate the total distance horizontally that this travels, okay, I'd have my horizontal velocity, which was this side of the triangle. I'd have my time, because I calculated over here, okay? And then I could just use v equals d over t to calculate d, and I know how far it is. Okay? If I want to calculate the maximum height, do I need anything from the horizontal part of this? No. Height's a vertical thing. Okay? So where in this flight does the maximum height occur?
The object gets to the middle part and stops moving.
Yeah, exactly. Right here, right smack in the middle. All right? Remember, from a vertical perspective, even though this thing has been thrown at an angle like that, from a vertical perspective, all the object is doing is this. It's going up and coming back down. Okay? From a vertical perspective, that's all that happens. So, okay, the maximum height occurs halfway through the flight. Halfway in terms of time. Okay? Now, here's the other thing to think about. How fast is the object going vertically at this point? 0. Right? This is the spot where it's at its maximum height, where it stopped for an instant before falling back down. So at the maximum height, the vertical velocity is 0. So I would know initial velocity, acceleration, and final velocity. I'd be able to calculate the vertical displacement, d, at that point. And I would probably use this formula. Okay? I would have one other option to calculate that d, and it would be to use this. I could also use that formula, because I would know what vi is, not 0, but I've calculated it already. I know what the acceleration is, and I know what the time is. But here's what people forget when they do it that way. How much of the time am I using? Half. Okay? So I would have to remember that whatever I calculated time to be down here, I'm only using half that number because it's happening halfway through the flight. Okay? You can make that mistake often. Which is why I advise people not to do it that way. If you do it this way, you don't have to use time at all. Just use A and D, which you already have. Okay? So that's how those are going to set up. We're going to work through a whole bunch like that. Okay? But first, we're going to watch some videos about projectile motion. Okay? Everyone's initial reaction is, boy, it's a good thing you hit that pool. He'd be dead if he hit that pool or not. Okay? I mean, that pool, you can buy those pools at Canadian Tire. Okay? They're like 6 feet across, and they're like 2.5 feet deep. They're a wading pool. If you flew through the air like that and landed in that pool, the only thing that would happen would be the structural integrity of the pool would fail, the water would go swooshing out, and you would break your back on the pallets of wood that it was sitting on. Okay? There is not enough water in that pool to cushion you from a landing from that launch. Okay? But people watched this, and people being people, went, that looks like fun. Is that for real? No. Okay? But again, people not being generally physics minded didn't think of that. And I'm sure lots of people tried to set this up and got hurt. Because, well, people. Okay? So, a lot of people sent this in to Mythbusters. Because they were big at the time. That was all they were doing, was busting all these internet myths, right? So, Mythbusters did a whole big episode. They built one of these things, okay? And they tested it. Just to prove that it was totally fake. Okay? So I'm going to show you now. They're doing their. So the thing with projectiles that are shot at an angle or launched at an angle is that you can actually predict or calculate where they're going to land. That's important if you're doing something like that Mega Whoosh thing, okay? Or if you're a stunt coordinator for a movie. Okay? If you want to launch a car and have it fly through the air and then have some, at least get some clip of it plausibly landing from behind, obviously not from in front, okay? You need to be able to predict where it's going to land. okay, based on how fast it hits the ramp, the angle of the ramp, okay, all of that kind of stuff can help you to predict where the landing will occur. This is also really important if you're in the military and you're in artillery. Okay, artillery is the big howitzers, like the cannons, okay, that launch the shells really long distances. Okay, the people that run those, they have to be accurate to within a couple of meters, and they can be. Okay, they can have people in the field, soldiers in the field, calling for artillery support and saying, "Here's my position, fire on my position," plus 6 meters. Okay, and they will reliably hit those kinds of accurate target things. Now, if they don't, then it becomes a friendly fire incident, then it's bad. Okay, but they can reliably hit those kinds of targets. Okay, just given, all right, I know how much powder I need to put in here, or I know how big the shell is, here's the angle of the cannon, and fire. Okay, and they can say, all right, it's going to hit right there. All right, so those kind of things come into play. They are things that we do almost by instinct if we're throwing a ball. Okay, if we're throwing a ball and we see somebody running, we want to throw it to them, we just kind of know by instinct, okay, I got to throw it fairly hard or at this angle or whatever to make it get there. Right? It's not something that we obviously calculate in our head on the fly, but it is something that we just kind of know instinctively. Okay? That making some sense? Okay. So let's have a look at this one here. Okay, so this is kind of what we just looked at, except it's a cannon and a cannonball. All right, so let's have you guys copy this one down. I'll give you a minute to copy it down, and then we'll kind of walk through how to do it. All right, so what we have in this question is this situation. We have a cannonball that's fired at 140 meters per second, 40 degrees above the horizontal. The cannonball is obviously going to follow a projectile arc, as all projectiles do, that will encounter the ground some distance away, some distance that we're being asked to calculate in this question. With all projectile motion problems, I need to make sure that I separate my vertical and horizontal information. The one thing they can share is time, because as long as it's in the air, it's moving both vertically and horizontally. As soon as it hits the ground, obviously both of those stop. Okay, so from a vertical perspective, before I do any calculating, I know this. The acceleration is negative 9.81 meters per second squared. Now I have to start doing some calculating. Okay. This side of my triangle represents the horizontal component of the launch velocity, or projected velocity. Right? If I want to calculate that horizontal component, then I'm going to go cos of 40 degrees times 140 meters per second. Right? That'll tell me how much it's moving, or how fast, sorry, it's moving horizontally throughout the entire flight, because it's not going to change its horizontal velocity. Okay, so it's moving at 107.25 meters per second horizontal. Okay. The other thing I have to remember is that I can also calculate how fast it's moving vertically, at least initially. Why only initially? What kind of motion is it experiencing vertically? Accelerated. Accelerated. So its velocity is going to change every instant after the time zero, right? So this is my initial velocity, how fast it's moving at time zero, and I would calculate that again using trig. Sine of 40 times 140 meters per second. All right, so 89.99. And that's positive because it is initially moving upwards. as long as the launch point and the impact point are level, what's the relationship between VI and VF? They're the same but opposite, right? So VF is negative 89.99 meters per second. What goes up must come down. Okay, I'm being asked to calculate two things. The maximum vertical displacement, which I can't get yet, okay, and the horizontal displacement. In order to get the horizontal displacement, I need speed and time, or velocity and time. Okay? Can I calculate the time with the numbers I have right now? I've got VI, VF, and A. Can I calculate T? Absolutely. Right, so time is going to equal VF minus VI over A, just a manipulation of our change in velocity formula. So that'll be negative 89.99 minus 89.99 divided by negative 9.81. Right, so I'm going to take that number there and just multiply it by 2. Okay, and then divide that by 9.81. Okay, so this thing is going to be in the air for just over 9 seconds. Okay, 9.17 seconds. Okay, so now I can calculate D. D will be 9.17 seconds times 107.25 meters per second. Okay, this thing's going to travel 980 meters. That's pretty far. Okay, and a cannon should be able to launch a cannonball pretty far. Okay, you don't need a cannon if you can throw it that far. So, okay, that's how we would work on that. All right, we'll look at the rest of this tomorrow, okay, and we'll run through some more as well as a few more examples of very, very bad movie physics.